last class we discussed about the kinematic parameters of industrial robots, and we mentioned that there are 4 parameters. The first one we called as joint parameter. The joint parameters define the relative position and orientation of 2 successive links, and they are the joint angle and joint distance. These are the 2 joint parameters, and they are defined as this is the joint distance, and the angle at which it has to rotate is known as the joint angle. So, they are defined as the rotation about the zk minus 1 to make axis xk minus 1 parallel with the axis xk. So, you have xk and xk minus 1 are the 2, k and k minus 1 are the 2 coordinate frames, so xk and xk minus 1. So, how much you have to rotate xk minus 1? So, how much this has to be rotated to bring it parallel to this is known as the joint angle, and that is with respect to the zk minus 1 axis. So, with respect to this axis, how much you have to rotate this in order to make it parallel to xk is known as the joint angle. And the joint distance is, so how much you have to move with respect to zk minus 1, how much it has to be moved to make xk minus 1 intersect with xk, and that is known as the dk or the joint distance. So, this joint distance and the joint angle completely define the relative position and orientation of these 2 links. So, that is how it is known as joint parameters. They define the position and orientation of 2 successive links. So, if you have any number of links, you can apply the same rule, you will be able to get theta k and dk, that is the joint angle and joint distance. So, this is what we saw in the previous class, and also I mentioned that if you consider it as a single degree of freedom, either d or theta will be a variable. So, if theta is a variable, it is a rotary joint, and if d is a variable, then it is a prismatic joint. So, one of this will be always a constant, the other one will be a variable. So, that is what we saw in the previous class about joint parameters. And then we discussed about the link parameters also. So, the link parameters basically define the position and orientation of 2 successive joints. So, we have 2 joints here. So, how these 2 joints are relatively positioned and oriented is given by the link parameters. So, one parameter is the link length ak, the other one is the link or the twist angle which we call as alpha k. So, these are the 2 link parameters, and they define the relative position and orientation of the 2 successive joints. And link length is the distance. So, link k connects k minus 1 to k, and then xk they are referred with respect to xk, that is the common normal between the axis k minus 1 and k, and all the parameters of link parameters are defined with respect to xk, that is the x axis of the kth joint, and that will be normally a common normal between zk minus 1 and zk. So, xk will be always a common normal between zk minus 1 and zk, and the parameters are defined with respect to that axis xk. Now, how they are defined? The ak, the link length, we call this as the link length, is the translation along xk needed to make zk minus 1 intersect zk. Okay, so, zk minus 1 and zk, how much it has to translate along the xk. So, if this is the xk, then along xk how much it has to move, and that is to intersect the zk axis, and that is known as the link length ak. And twist angle again measured with respect to xk. If this is xk, twist angle will be measured with respect to xk. What is the rotation of zk minus 1? So, how much this k minus 1, it is like this, how much it has to be rotated to make it vertical. So, in this case it is vertical. So, how much it has to be rotated with respect to xk is basically the twist angle. Okay, so, the twist angle alpha k is the rotation about xk needed to make zk minus 1 parallel to zk. So, that is basically the twist angle alpha k. Rotary joint, it is like this joint. Okay. The other one is this joint. Got it? One is this, the other one is this. So you have a vertical axis, rotational axis, and you have a horizontal axis. Now the question is, suppose this is xk, so how much this has to be rotated to make it like this? Okay, so that is the twist angle, and how much this has to travel in order to intersect with this is the distance, length. Okay, yeah. So these are the 4 parameters. So we have now ak, alpha k, and then we had theta k and dk. So these are the 4 kinematic parameters associated with every joint. Okay. Pardon? Which one? You mean acute in the sense? No, you mean to say plus or minus or 90? You are asking whether it can be 60? Yeah, see, technically it can be 60 or anything, but normally we will make it into 90 degrees. The alpha will be normally multiples of 90 only, because then you can actually have another direction of motion. If you make it 60 or something, then you won't be. You can still do it theoretically. You can do, but your kinematics will be much more complex, because alpha, depending on alpha, you may not be getting the xy another degree of freedom completely. Because then you have a one joint like this and one joint like this, are actually moving into a different plane. But if you make it 60, you won't be able to completely move to that different plane. So you may not be getting a full motion in that case. So normally we'll make it alpha will be 90 or multiples of 90 you can have. No, positive or negative depends on from which direction you are looking at. So it is convention is that anti-clockwise is always positive. No, now I will tell you. See, this is xk. Okay. Now you look from here. If you look from this xk, now I am rotating it like this. Okay. So it's a clockwise motion. So it will be minus 90. Sorry, yeah, minus 90. Anti-clockwise is always positive. So which xk? So I am looking from xk, and then it has been rotated like this. So it has moved a clockwise motion. Therefore, it will be 90. Minus 90 degree. Okay, anti-clockwise is taken as positive. Any questions? Anyway, we'll be going through this because when we do the forward kinematics, multiple of this will come. I didn't get your question. No, we are always saying zk minus 1 to zk. See, we are telling that make axis zk minus 1 parallel with zk. So we are always rotating zk minus 1 to make it parallel to zk. Yeah. Okay, so these are the 4 parameters, and we saw that theta k or dk, one of this will be variable. Only one of this, one will be a variable, and the other will be constant. And this ak and alpha k, for a given manipulator, once you designed a manipulator, this will be constant. You cannot change this because the robot configuration, whether it is a Cartesian or articulated or whatever the configuration, we will fix this because the link length, everything will be fixed for the design. So once we have already designed the robots, then ak and alpha k will be constant. So out of these 4 parameters, only one parameter will be varying for every joint. So that can be either theta or d. So it's a rotary or prismatic joint. So that parameter only will be varying, all others will be constant for a given manipulator. So that is the thing here. Out of the 4, out of these 2, these are always constant because they are part of the mechanical design. So you have already designed it. So the mechanical design decides what should be the link length and what should be the twist angle. So basically, where do you want to join? You want a joint like this or like this will be always decided, and what should be this length also will be decided by the mechanical design, and therefore you will see that they are mechanical parameters and that will be always fixed for the given manipulator, and the only thing that you can change is this joint angle. So once you change the joint angle, then only the position varies. So if you want to change the position at this tip, then I can change any one of these angle. I can change this angle, or I can change this angle, or I can change this angle. Of course, in this change this angle, I don't change the position, but I change the orientation. So this way, always there will be only one parameter which will be varying, all others will be constant. Out of these 4, 3 will be constant. So this actually shows an animation, but I think I already explained all these to you. I'm not sure whether it will work. Let me check. Somehow it's not working. Don't worry. It's okay. Oh, okay, it's working now. Yeah. So basically, it talks about getting the common normal and the x-axis, and then finding out the distance traveled in along the zk minus 1. So this is along the zk minus 1 travel, that is the dk, and this is along the xk, which is the ak, and the angle between this axis and this axis is alpha, again with respect to measured with respect to this axis. So these are sometimes known as DH parameters also, Dynavit and Hartenberg parameters, because Dynavit and Hartenberg long ago they came up with a methodology for getting the systematic kinematic analysis of serial linkages. So they are called as DH parameters also. So we will be using these parameters in the forward kinematic analysis. Okay, so to summarize, we have theta, d, a and alpha, and this will be variable for revolute joints, and if it is a prismatic joint, this will be fixed. Similarly, this will be fixed and this will be variable for a prismatic joint, and all others will be fixed. So for an n-axis robot, so now you know that for each axis you will be able to get the 4 parameters. So when you have a n-axis robot, you will be having 4 n parameters associated with the robot. So if you have a 6-axis robot, you will be able to see, you will be able to get 24 parameters attached as part of the kinematic parameters of the robot. So for each axis, you will be having these 4, and these parameters will affect the position and orientation of the tool. When you have multiple joints, each parameter will be having its own influence on the final position and orientation. So the question is, how do we actually get the final position, or how do you get the kinematic configuration of the robot, and that actually will be getting by this. So these 4n parameters decide the kinematic configuration of the robot. Any question on the parameters, the kinematic parameters? Yeah. Numbering in the sense k. Oh yeah, we are coming to that. Now we will be discussing about how do we actually systematically assign the, find out the parameters of a n degree of freedom robot. We will discuss that. That is part of the kinematic analysis. Okay, so before going to the kinematic analysis, just want to tell you this. So we mentioned about the 3 angles that we can represent as the orientation, yaw, pitch and roll. So this yaw, pitch and roll basically represented in terms of 3 angles, but we can actually represent it as each one as a vector also. So the configuration of the tool in Cartesian space is normally represented using a 3×3 matrix. So the orientation. So we will be having one vector here, another vector here, another vector here, and this one we call as the normal, sliding and approach vectors. Because this YPR, yaw, pitch and roll, change the orientation, and the orientation can be represented as a vector, and they are the normal, sliding and approach vectors, NS, NS, NA. So the approach vector is along the z-axis, and this is along the y-axis, and this is along the x-axis. So the normal is the x-axis with respect to x-axis, and this is the y, and this is z. So that is the normal, sliding and approach vectors. So normally, if you want to specify the orientation of a tool in Cartesian space, what we do is we will write it as nx, ny, nz. Similarly, sx, sy, sz, ax, ay, z. So, this is the orientation that we can specify in Cartesian coordinates, and if they are aligned with the base frame, then you will be getting it as 1, 1, 1, 0, 0, 0, 0, 0. So, if the tool frame and the base frame are aligned, you will be getting it as 1, 1, 1. If they are not aligned, you will be getting this kind of a matrix, non-zero elements here, and that depends on how much you have rotated, the coordinate frame has rotated with respect to the axis or yaw, pitch and roll. So, you can represent either using the angles or using a vector like this. That is why. So, most of the time we will represent the final orientation that we want the tool to have in terms of these vectors, and then we will try to find out what joint angles will actually give you that kind of a motion. Okay. All right. So, once you have understood this, what we need to do is to go to the, okay, so I already mentioned these things, so it is not clear. So, approach vector is aligned with the roll axis, and sliding vector is orthogonal to the approach vector, and yaw, pitch, roll motions are motion rotation about normal, sliding and approach vectors. So, that is what this one says. Okay. So, we found the, we saw how to get the configuration of a robot based on the type of joints and the number of joints, and then we saw what are the parameters that actually will define the kinematics of a robot. Now, the question is, by knowing these parameters, how do we actually develop the forward kinematic relationship or the kinematic relationship? So, first we talk about forward kinematics, and then we go to the inverse kinematics problem. So, as I mentioned in the previous class, so I already mentioned about this direct or the forward kinematics problem. So, given the joint variables of a robotic manipulator, now we know what is joint variables because we defined the parameters and we found that either theta or d can be a variable. So, if you know these joint parameters corresponding to each joint, so if you have an n axis, then you will be n joint variables. And if you know these joint variables, how to determine the position and orientation of the tool with respect to a coordinate frame attached to the robot base. So, this is the basic forward kinematics problem or the direct kinematics problem. So, what we know is theta, and of course, we need to formulate the kinematic problem in such a way that though the 6n parameters are involved, so we know that okay, 4n parameters are involved totally. Out of these 4n, we have only n parameters varying. So, the other 3n parameters will be constant. So, if we know these 3n parameters, we can have a formulation where these parameters can be assigned, then you will get the final relationship for the forward position of the robot. So, that is what we need to develop. So, how do we do this? So, we need to have a very concise formulation. It's a general solution to the direct kinematics problem. So, for any robots, whatever may be the configuration of the robot, we should be able to develop this relationship based on the parameters that we identified. So, that is a concise formulation which we call as the forward kinematic relationship or forward kinematics problem or direct kinematics problem. Okay, so how do we do this? Suppose we have a robot configuration given to us. First thing what we need to do is to assign a coordinate frame to the robot. So, the problem is that suppose this is the tool and this is the base of the robot. So, I can fix the face somewhere. I want to know for different giant variables of theta, I call the generalized variable as theta. For various values of theta, what will be the position and orientation of the tool is the problem that we are trying to address or trying to formulate. So, as a first step, so we call this as the Dennavit and Hardenberg representation. So, that is the method we will be following, Dennavit and Hardenberg or DH representation. So, the first step to do is to assign coordinate frame for all the joints, because we know that when this joint is moving, all this gets affected. When this joint is moving, all this gets affected. and with respect to the base, the position changes with respect to, I mean, whenever there is a change in any one of these variables. So, to take care of all the joint variables, what we do, we try to assign coordinate frame at every joint. And finally, we try to find a relationship between this coordinate frame and this coordinate frame using coordinate transformation matrices and get the relationship. So, suppose this is the robot configuration given to us. What we do is we will try to make a simple free body diagram and say that it is a home position of the robot, because robot can take any position. This angle can be anywhere, this can actually change. So, it can be in any position, it can be like this, it can be like this, or it can be like this. So, we consider a home position and then try to assign the coordinate frame. So, what I will do, I will assume that there is a joint here and there is a link here, then I know there is a joint here, and then there is a joint here, and there is a joint, and like this, and then I will finally say, okay, oh, this is the robot configuration. So, I will make a home position. It can be any position, does not really matter. You can actually have whatever the you want to put it like this, or you want to put it like this, you can have. So, I will have a home position like this, and then try to assign coordinate frame for this configuration. So, first one is I will assign a, okay, this one I already explained. So, this we call this the number of the joints from 1 to n, starting with the base and ending with the tool yaw, pitch and roll in that order. Okay. So, we will say that, okay, this is J1, this is J2, J3. You can write 1, 2, 3, 4, etc. That is the joint, and the last joint will be nth joint. So, if you have 6 degrees of freedom, you will see that 6th one is the roll axis. So, the roll joint is the 6th one or the last one, and 1 to n. So, start with J1, J2. So, this is 1, 2, 3, etc. That is the first step. Now, okay, so I will remove this. Now, give the link numbers also. So, we will start with the link 0 and link 1, link 2, link 3, etc. So, link 0 and 1 connected by joint 1, 1 and 2 connected by joint 2, like this. Okay. Now, see, the robotic researchers follow different styles. Someone put this as link 1 and then put as link 2 also. So, if you are following a particular convention, you can keep following that, but if you have following some other convention, then you need to keep following that. Finally, the results will be the same, whatever may be the link numbering you are taking, the results will be the same. So, for example, if you refer Craig is the book, or you refer Schilling, there will be some difference in the way the coordinate frames are assigned and the numbering is done. So, I follow the Schilling convention. That is why I am doing this link 0, 1, 2, etc. But if you follow Craig, there may be slight difference, but the formulation, final formulation will be the same. So, but try to follow one of these, otherwise you may find it a bit difficult if you mix up these things. All right. Now, so J2, J3, etc. we have till J6, whatever it is. Now, first thing to do is to give a base coordinate frame assignment. You need to assign a base coordinate frame based on your convenience. Okay, you can have it as whatever way you like, but you need to follow the right hand rule. The right hand rule is that if this is x, then this is y and this is z axis. So, this is known as the right hand rule. So, you always follow the right hand rule for assigning coordinate frame. So, if I put this as x, this as z, okay, so this is x0, z0, y0 will be inward. So, it will be, so you will always follow this rule. So, if I fix this as x, y, z, then it will be easy for us to analyze it later also, how the rotations take place. Okay, so yeah, this is my x axis, this is the z axis, and this is the y-axis. So first thing is, okay, so we'll call this as the base coordinate frame, and we call it as L0. That is the base coordinate frame L0. So assign a right-handed orthonormal coordinate frame L0 to the robot base, making sure that Z0 aligns with the axis of joint 1. That is very important. So you have to see what is the axis of rotation. Here you can see the axis of rotation with respect to this. The first joint rotates with respect to this axis, and therefore I will align the z-axis along that, and then x-axis I can take x-axis this direction or this direction, any direction. For my convenience, I take in towards the positive direction of the robot, just for convenience only, so that I will get it as a positive value for the position. But you can actually decide x0 whatever way you like to do it, preferably to take it in the positive direction. So this will become x0 and then y0 you will get. So you know z, how to get the z-axis, and then x can be decided based on your convenience, then you get the y-axis. Okay, I said k is equal to 1. So this is L0, x0, y0, z0. That is the base coordinate frame L0. Now k is equal to 1, we get the coordinate frame L1. So we need to get L1 as the next coordinate frame, and the next coordinate frame basically represents the joint 2, or with respect to what point the joint 2 rotates. So we are defining a coordinate frame L1. Okay, now let me remove this. Okay, that is the x0, z0 and y0 frame. So the first thing is align the z-axis with the joint axis, and then get x and y based on the right-handed coordinate frame. Okay, the next one is align z-axis with the axis of joint k plus 1. So now find out what is the next z-axis or z1, and align the axis of joint k plus zk with the joint k plus 1. So the joint 2 is this one. So we need to find out what is the joint axis here. What is the joint axis? Okay, inward or outward. Okay, you can take any direction. You can take outward or inward. So I am taking, for the time being, I am putting it like this. So I will say this is my Z1. That is the Z1 axis. Now we need to find out the origin of the coordinate frame L1. So this is part of L1, but the origin need not be at the joint. Okay, so there is no need to have the origin of the coordinate frame at the joint. It can be somewhere else also. So to get the origin, what we do is we try to find out where this Z0 and Z1 are intersecting, where Z0 is intersecting with Z1, and that will be the origin of the next coordinate frame. Okay, so locate LK. So now k is equal to 1. So locate L1 at the intersection of ZK and ZK minus 1. Okay, so ZK and ZK minus 1 intersect at this point, and therefore your origin of L1 will be that point. So now we got the origin and the z-axis. Now the next question is you get to get a, okay, in case they are not intersecting, find a common normal between Zk and Zk minus 1 and see where Zk is intersecting with that common normal. Okay, so if they are parallel, we will see that case next case. So if they are parallel, they are not intersecting, then you find a common normal and then see where Zk is intersecting with that common normal. That will be the origin of the coordinate frame. Who can we have? You mean when can we have such a situation? No. We'll see, look at this joint. Okay, I am coming to that, so I don't want to jump to that. Okay, we will see that case where actually they are parallel. Okay. So LK, we fixed the origin of L1 and we identified the z-axis also. Now we need to find out what is x1. Okay, what is the direction of x1? So x1 should be always normal to orthogonal to z0 and z1. That is the requirement. So xk to be orthogonal to both zk and zk minus 1. So now this is one direction, the other one is in this direction. So it has to be in this direction only. Okay, xk should be along this direction because it should be orthogonal. So your z0 is this direction and z1 is in this direction. So it has to be xk should be in this direction. So your xk will be in this direction. And then now you have a xk. Okay, so this is xk. Yeah, this is xk, this is zk, and therefore your yk from the right-handed rule, yk will be like this. So yk will be this. So your y-axis will be like this. So x1, z1, and y1 you identified the coordinate frame. So always follow the right-hand rule, then you will always get it. Because now your z is like this. So this is the x. This is x, z, and then y will be downwards. Okay. And again, they are parallel, point xk away from zk minus 1. So if they are parallel, move it out of, because both will be the same direction. If zk and zk minus 1 are in the same direction, then away from this you point it. That is the direction you can take. So we found that, okay, we can follow this algorithm to get the first joint and its coordinate frame, and then the second one joint and its coordinate frame can be obtained. Now we can follow the same thing, change k is equal to 2, we will be again getting the next one. So you can keep on doing this till you reach the last one. Okay, last one we will do it in a different way. So till k is equal to, so yk from right-handed coordinate frame Lk, and then set k is equal to k plus 1, and as long as k is less than n, go to step 2, continue. So now suppose I want to get L2. L2 is the next coordinate frame, that is at J3 you have L2. Okay, I don't know where actually L2 is, but I know coordinate frame is L2. So I need to find out the coordinate frame associated with the joint 3. So what will I do? What is the first step? First step is align zk with the axis of joint k plus 1, right? So what is the joint axis here? Assume that this is the same kind of joints. So I will be having Z2 here, right? Yeah. See, when they say it's outside, basically I am telling it is 180 degree apart. My z axis is rotated by 180 degree. I can take this direction or this direction. It is optional, but normally we try to reduce the rotation in the frame, but you can still have it as this direction, or you can even assume this direction. Nothing wrong in assuming this direction. So basically I am telling, here I am telling there is no rotation. If it is this direction, I am telling there is a 180 degree rotation, z axis, between two z axes, z1 and z2, 180 degree apart. Okay. Okay, so we got the z axis. Now we have to find the origin of the coordinate frame. How do we get the origin? Intersection of z1 and z2, right? So you want to find out an intersection of z1 axis and z2 axis. Where is the intersection? There is no intersection, right? So what will we do? Because they are parallel. So when they are parallel, what is the strategy? Common normal. So you find a common normal and then see where the common normal intersects Z2. Okay. So, the common normal will be always this, and it intersects here, and therefore, your origin will be L2. So, that will be the origin L2. Now, you assign x axis because x should be away from Z1 because they are parallel. So, x should be away from Z1. So, we make this as x2 and then give the same as y2. Keep on doing this till we reach k is equal to 6. So, k, if this is a 6 degree of freedom, so k is equal to 6, we cannot follow this. Till k is equal to 5, we will be able to do this. So, we will be keep on assigning the coordinate frames like this. And when k is equal to 6, you have to follow a slightly different one. Basically, that is the tool point coordinate frame. The last one will be the tool point coordinate frame because L0 is the first join. So, L6 will be the last point, that is the tool point coordinate frame. Okay, so this is the way how you get it. And the last one, set the origin Ln, that is the L6, that is the last origin of the coordinate frame, last coordinate frame at the tooltip. Set the origin at the tooltip. So, I will set the origin L0 or L6 at the tooltip, L6. Align Z6 with the approach vector. Okay. So, the approach vector is the roll axis. So, if this is rotating or rolling, then this will be my Z axis. That is the Z axis, last one, L6 or L5 depending on the number of join. If it is a 5 degree of freedom, then it will be different 6 degree of freedom, but n is equal to 5 or 6 depending on whether it is a 5 or 6 degree of freedom robot. Then approach vector yn with the sliding vector. So, the sliding vector is this, it is sliding. So, open close section is known as sliding, and the normal one. So, based on the x, y, z, this 2, y and z, you will get the x also using the right-handed coordinate frame, coordinate rule. So, this way the last coordinate frame will be decided based on approach vector, sliding vector and the normal vector. So, z, y and x will be approach, sliding and normal vector. So, that will be decided based on that, no other rule. Till then, we will follow the rules what we discussed, and the last one will be assigned like this. So, finally, you will be getting the point, all the coordinate frames assigned. So, you will get all the coordinate frame assigned like this. That is the first step in getting the DH formulation for forward relationship. Any questions? No, it need not be a unique one. The assignment of coordinate frame need not be unique, but the final formulation will be unique for that particular robot. Okay, whatever you do, your alpha, theta, d and all will decide how you do this. For example, instead of this in this direction, if you have decided in this direction, so this alpha will be 180 instead of 0, and that will actually affect your final calculation. So, that way you can have different assignment of coordinate frames, and your DH parameters also may be slightly different because of that, but the final result will be the same. Okay. No, see, this is not complete because it's actually a 5 degree of freedom robot. I just shown only 3 joints here. 2. Yeah. Yeah. So, that is why I am telling, if it is 5 degree of freedom, then it will be L5 that will be coming at the tip. But assign coordinate frame will assign based on this. Okay, whatever may be the number of degrees of freedom available, it is only 2, but still we need to have a coordinate frame with XYZ coordinates. Because the final orientation depends on what is the way it is oriented with respect to XYZ axis. Okay. Any other questions? So, now the final requirement is that we need to find out this position. So, assume that this is the tool position we are interested. We need to know how this actually moves with respect to this. So, we need to have a relationship how this coordinate frame will change its position and orientation with respect to this base, that is to be decided. So, we can actually say this is a position vector, there is a position vector which actually decides the position of the tooltip, and there is an orientation which decides what is the way in which this is oriented. You can see the z-axis is like this, but here it is like this. So, there is a rotation of this coordinate frame with respect to this coordinate frame, and that actually depends on all these joint motions. All these joint parameters will affect the position and orientation. We need to have a concise formulation which will take care of all these elements, and then give you a formulation. So, I will take another 5 minutes to tell you a few more steps involved in this formulation, then we will stop here. Okay. Now, we define few points, there are some virtual points, there is not physically any relevance, but to get the DH parameters, we need to define some points. So, we define point BK, assume that BK is now k is equal to 1, so BK will be B1 at the intersection of xk and zk minus 1 axis. So, x0 and x1 and z0 where they are intersecting, that point we define as B1. So, you can see that the x1 is here, x1 is here and z0 is here. They are intersecting at this point. So, we call this as B1. Now, if you want to find B2, what will be B2? Where will be B2? X2 and Z1. Where are they intersecting? X2 and Z1. Where will it be? Okay, this is X2, this is Z1. So, it will be here only, right? So, B2 also will be here. It has got some significance in calculating the parameters. So, like this you get B1, B2, B3. So, this will be B3 and then it will be gone like this. So, you will be getting all the BKs. Now, once you have this B1, B2, B3 etc., how do you get the theta k? So, theta k is the angle of rotation from xk minus 1 to xk measured about zk minus 1. That is theta k. You have to find out what is the rotation of x0 to x1 with respect to z0. So, x0 to x1, if there is any rotation, that will be theta k measured with respect to this axis. So, you have to look from this axis and then see whether it is rotating clockwise or anti-clockwise. You will be getting theta k. Theta 1 will be x0 to x1. So, x0 to x1, what is the angle? So, what is the angle here? What is the rotation of x0 to x1? 0, right? So, in this case, so current configuration theta 1 is equal to 0. That is all. Okay, it can actually change. You can actually rotate it, then x1 can be in a different orientation. You will get theta is equal to 90. When it comes out, it will be theta will be 90 also. And similarly, you can get theta 2. So, what will be theta 2? Theta 2 is x1 to x2 with respect to z1, right? Again, it will be 0. Since it is in a home position, we have got everything as 0. But if you change this, if you rotate this or this, you will get a different joint angle also. Okay. So, theta 2 is 0 in this case. Similarly, you will be able to get all the joint angles. So, whatever may be the rotation, you can get using this rule. Now, dk as the distance from the origin of frame LK to point BK measured along ZK minus 1. Okay, that is the joint distance we will call. So, joint distance is the distance from this frame to this frame. So, L0 to B1, L0 to B1 measured along Z1, Z0. So, L0 to B1, right? Yeah. D1. L k minus 1. I think this figure is this k minus 1. Okay. So Lk minus 1, okay, that one has gone to this side. Okay. So Lk minus 1 to Bk. So Lk minus 1 is this, L0 to B1 measured along this axis is known as the dk. So this is the distance d1. L0 to B1 measured along Z0 is dk. And similarly, you will be able to get d1, d2 also. So d1 we found something, the length. D2 also you will be able to get. But you will see that B1 and B2 are here. So L1 and B2 are at the same point. So you will see that D2 is equal to 0. Because B2 and L1 are at the same point. So L1 to B2 there is no distance. So D2 will be 0. And then AK is the distance from BK to LK. B1 to L1, B2 to L2, B3 to L3 measured along XK. That is the AK is the distance. So if you want to get A1, so A1 will be the distance from L1 to B1 measured along X1. So what is the distance from L1 to B1? 0, right? So in this case, A1 will be 0. What will be A2? A2 is L2 to B2 measured along X2. So B2 is here, L2 is here. So L2 to B2 is the distance. So this will be the A2. The distance, this will be the distance A2. And finally, alpha as the angle of rotation from Zk minus 1 to Zk measured along Xk, measured about Xk. So you have Z0 and Z1 measured about Xk, X1. So assume that this is Xk. So you are okay, this is Z axis. Yeah, Z axis pointing. So this is your X axis. So if you, this is X2, this is X2. Now how much Z0 has rotated to come to this position? So Z0 was like this. Now it has rotated like this to come here. So if I am looking from X2, it has rotated from here, this position to this position. So you have a 90-degree rotation in the clockwise direction. So alpha k will be minus 90 degree. Okay, the alpha 1 will be minus 90 degree. Similarly, Z1 to Z2, you will see that there is no rotation, they are parallel. So alpha 2 will be 0. Z2 to Z3, you have to see the same logic you apply and you will be able to get the parameters. So this way, you will be able to get all the 4 parameters theta k, dk, ak and alpha k for every joint. So if you have 6 joints, 6 axes, each k is equal to 1 to 6, you will be able to get all these 4 parameters. So finally, you will be able to create a DH matrix or DH parameter matrix of that particular robot. So for a given robot configuration, you will be able to get this DH parameters using the DH algorithm what we discussed. Okay, so this is the way how we assign coordinate frames for the manipulator and get the DH parameters for all the joints. So all the joints, we first assign coordinate frame based on the right-handed coordinate rule and the method mentioned, and then once you have this, then assign BK, and based on this you get all the parameters, joint parameters for the joint and link parameters for the robots, and that will give you the first step in getting the kinematics, forward kinematics solved. Okay, so please go through this. You may find it a bit complex by looking at it, but Once you understand the basic principle, then you will be able to get it very easily. Just by assigning coordinate frames, you will be able to get the parameters. Now, we will do few examples to make sure that you are comfortable with this, and then we will be having a tutorial session on Thursday to solve some problems also. Okay? Any questions? All right. Thank you. So, I will meet you tomorrow.